It is now time to understand a very common problem found in engineering textbooks wherein the stresses developed due to thermal expansion is studied. So here we see that we have a bolt and a sleeve assembly which are held by these two stoppers and tightened here. Okay. Now let us first understand what is thermal expansion. So when we heat a body, it has a tendency to elongate based upon its coefficient of thermal expansion. So if the body is held free, it will elongate and no thermal stresses will be set up. But if there is something that is restricting the body to freely expand, obviously stresses will be set up in the body. So we'll study this problem of statically indeterminate structure with the help of this sleeve and bolt assembly. Now let us analyze the situation. See, here we have the sleeve which has the thermal coefficient of expansion as alpha S and the bolt which has the thermal coefficient of expansion as alpha B. Here obviously it is given the problem that alpha sleeve is greater than alpha B. That means that the thermal coefficient of expansion of the sleeve is more than that of the bolt, which will mean that when subjected to the same temperature change, the sleeve will expand more than the bolt. Okay, so now let us analyze the thermal effects. We are seeing here that when the bolt and sleeve assembly, which is held by these two stoppers and tightened by this nut, is subjected to a temperature change of del T, we find that when they are left free, they would expand by del Ls, the sleeve will expand by del Ls, and the bolt will expand by del B. Okay, so these are the free expansions when subjected to the thermal load, that is del T. Del Ls anyway can be quantified as change in length of sleeve due to thermal expansion is alpha sleeve into length of sleeve into change in temperature. Similarly, the change in length of the bolt is written as del LB is equal to alpha B, length both were having the same initially, and change in temperature. So as we have already seen in this problem that alpha sleeve, that is coefficient of thermal expansion of the sleeve, is more than that of the bolt, obviously the sleeve will have a larger expansion when it is set free. So here we see that the free expansion of the sleeve when subjected to temperature change of del T is del Ls and free expansion of the bolt is del LB. Because they are held together by the assembly, hence thermal stresses are developed. I told you that thermal stresses do not develop until the body is free to expand. Only when it is held together or stopped from expanding, thermal stresses will develop. So now we are seeing that these two, which are having different coefficient of thermal expansion, and when they are set free they will expand differently, are held together by these two stoppers, and they are not set free to expand. So obviously thermal stresses will be set up. When the thermal stresses are set up, the forces existing in the sleeve and the bolt in the original assembly must be such that they shorten the sleeve and stretch the bolt until the final elongation of the sleeve and the bolt are the same. So since I told you that due to free thermal expansion, if they are set free, they will have different expansions. But since they are stopped by these two stoppers, they will have same expansion, because of which actually the sleeve will get shortened or compressed and this bolt has to be lengthened or axially stretched. Okay, so let us analyze the problem and find out what are the stresses that is acting on these two sleeve and bolt. First, we'll try to find out the static equilibrium condition. Static equilibrium condition. So with the help of static equilibrium condition, we can see at this support, the compressive load applied on the sleeve by this stopper, that is PS, will be equal to the tensile load that is applied on this bolt, that is PB. So this is our first equation for finding out the loads or the stresses acting in this bolt and sleeve assembly. PS is equal to PB. But here we see that we have only one equation and we have two unknowns to be found out. So it is now a problem of statically indeterminate, for which we'll start making the compatibility equation. compatibility equation. So we'll closely watch as to how compatibility equation will be applied here. When sleeve is allowed to freely expand, it will expand up to del ls, and when the bolt is allowed to freely expand, it will expand up to del lb. But since these two are held together by the stoppers, the differential expansion will not happen, and these two will have to expand together, for which actually let us suppose that this is the final length, okay, wherein the sleeve has to be compressed and the bolt has to be stretched to reach this position. Okay, so we have to equate to del L. Del L will be equal to change in length of the sleeve, that is del Ls. This is del Ls minus this. Minus this. What is this? This is the change in length due to the load applied by this stopper. So change in length anyway will be PL upon AE, that is load applied on the sleeve, PS. Length of the sleeve, that is L only, because we have taken initial length L, same for both. Area of cross section of the sleeve and Young's modulus of elasticity of the sleeve. So change in length, we can see that this is the final. If suppose here it was our assembly was there, so this is free expansion, and finally due to this stopper it will stop here together. Okay, so del L is the final change in change in length for these two. So del L will be equal to change in length of the sleeve when it is set free to expand due to change in temperature minus the change in length due to compression applied by this stopper. Okay, so change in length due to compression will be PS into L by AS into ES. This again we can see that when the sleeve is brought to this condition, wherein del Ls minus this sleeve is brought to this condition, this bolt also has to be stretched to reach this position. Okay, so del L will be equal to del Lb, that is change in length of bolt due to free expansion, plus, see, because they both have to expand together, this bolt has to be stretched to reach this point. Okay, so what will be the stretching, change in length due to stretching is equal to load in the bolt, load applied on the bolt into initial length of bolt divided by area of bolt into Young's modulus of elasticity of bolt. So this is our compatibility equation here. This is our compatibility equation. Now we can substitute del Ls and del Lb by these. So it will be alpha, I'll use blue pen, alpha S L del T minus PSL upon AS ES is equal to alpha bolt L del T plus PB to LB by AB EB. Okay. Now since we already know that PS is equal to PB by the condition of static equilibrium, we can substitute here, and by rearranging we'll find that alpha S minus alpha B into del T into L is equal to PL 1 by AS ES plus 1 by AB EB. Okay, so we can cancel L on either side, and P can be written as, I'll write the black pen to differentiate, P can be written as alpha S minus alpha B into del T by 1 by AS ES plus 1 by AB EB. So this much load the stopper has to apply on the bolt and the sleeve to hold it together and not allowing to expand freely these two bolt and sleeve assembly. Okay, so here is the load that we have found out using two equations, one derived from static equilibrium condition and the second derived from compatibility equation. So we got the formula for load. Now our target is to find out the change in length. We'll take a separate page. Now see, what will be the change in length? Change in length can be calculated either way, either by subtracting this from del Ls or by adding this to del LB. Okay. So we'll take either of them. So this delta or change in length can be written as del LS, that is change in length of sleeve due to free thermal expansion, minus compression, change in length due to compression applied by this stopper, that is PS LS upon AS ES. Okay. Del LS can be written as alpha S del T into L minus, now this P we already know, see, PS is equal to PV is equal to P, and formula for P we have already derived. So we can write P as alpha S minus alpha B del T into L by 1 plus AS ES plus AB EB. For easiness of calculation, we'll consider K is equal to AS ES by AB EB. This we are just taking for easiness of calculation. Okay, so now we'll write this as alpha S del T into L plus K alpha S del T into L minus alpha S del T into L plus alpha B del T into L, which is now divided by 1 plus K. So here we find that alpha S del T into L and alpha S del T into L will be cancelled. So we'll be cancelling it. I hope it is visible. Yeah. So we can write this as del T into L into K alpha S plus alpha B divided by 1 plus K. And when we substitute the value of K from here, we'll find change in length, I'll write by another pen, change in length, that is del L is equal to AS ES alpha S plus AB EB alpha B by AB EB plus AS ES whole multiplied by del T, that is change in temperature into initial length. So this is our final change in length. When a bolt and sleeve assembly is subjected to change in temperature and not allowed to freely expand, but it is bound by this assembly.